In our previous lecture, we were discussing about some of the important statistical characterizations of turbulent flow, and we will just continue with that. We were discussing about the correlation coefficient towards the end of the previous lecture, and that we defined as follows. We have to keep in mind here that this is not like the most general definition of a correlation coefficient, but this is a special type of correlation coefficient which we call as autocorrelation coefficient. So, what is the autocorrelation coefficient? If you have a random variable say at some instant of time, here we are talking about some instant of time at a given location, and the same random variable considered at the same location at a different instant of time, say t plus tau, then how those how the outcome of the random experiment based on the random variables they are correlated. If the random variables are same, it is known as autocorrelation. So, it is based on the correlation between the outcome of the same random variable just at different conditions. One is at t, another is at t plus tau, and here the random variable is u prime, which is the fluctuation component of the velocity along x. So, this sort of indicates that how strongly the outcome of the random experiment in terms of the random variable u prime here at a given point at two different instants of time are correlated. So, if you have for example a plot of this r tau versus tau, when tau is equal to 0, you see that you are talking about the correlation of the random variable u prime at a time t with itself at time t, and therefore they are exactly the same, and it is clear from the expression also that the correlation coefficient is 1. So, this autocorrelation coefficient is 1 at tau equal to 0. As you increase the tau, you are having the correlations of the same random variable at two different instants of time which are differing from one another, and in that way the correlation coefficient will tend to get reduced. Beyond a threshold time limit, you see that the correlation coefficient is really very small, and to get a feel of the time scale over which the variable is strongly correlated with itself at just a different instant of time, we may consider the following. So, if you find out the area under this curve, that is basically integral of the correlation coefficient from tau equal to 0 to infinity. So, that is area under the curve. Now, if we have a very strong correlation, say correlation coefficient equal to 1, but lasting over a period of time which is different, say lasting over a period of time given by this tau I, such that the area under the rectangle which is tau I multiplied by 1 is same as the area under the previous curve, then what it shows is that tau I is obtained as a time scale, a representative time scale over which the variables may be thought of to be very strongly correlated, and that may be obtained from the integral of the correlation coefficient, and this tau I is known as integral time scale. So, integral time scale physically is a representative time scale over which a random variable, here the random variable is the velocity fluctuation, the random variable is strongly correlated to itself as an outcome of the statistical averaging over the random experiments. Similar scales may be obtained by considering the other types of correlation functions such as cross correlation functions, where maybe you are trying to find a correlation between u prime and v prime. So then u prime has to be replaced with v prime, but we are not going into all those details. Our main emphasis here is to develop a building block for the basic statistical analysis or statistical description of turbulent flows. The big question remains that why should we at all go for the statistical description of the turbulent flows, and we actually tried to answer this question in a part of our previous lecture, that when you have a turbulent flow, the governing differential equations, for example the Navier-Stokes equation, they are very much valid. Only problem in implementing the governing equations as the Navier-Stokes equation to solve for the velocity, pressure and so on is that number one, there are multiple length scales and time scales. So you have the largest length scale over which any important physical phenomenon taking place as the system length scale, and as you go down you will find that the smallest length scale is the Kolmogorov length scale, which is much smaller than the system length scale, and there is a whole lot of physical activity engulfed between these largest and the smallest length scales, and all these length scales and similarly all the different time scales, they need to be captured quite accurately, so that resolution of the scale is important. Even if that is resolved, the second question is how reliable are the results, because the results will strongly depend on what? The results will strongly depend on the following: how reliable are the input data. So when you say that how reliable are the input data, it obviously depends on many things. The first is how reliable are the initial conditions, how reliable are the boundary conditions. So how reliable are the initial or the boundary conditions, these depend on the randomness of the physical behavior, and in turbulent flows the randomness of the physical behavior is very strong. So when the randomness in the physical behavior is very strong, the only way in which you may have a sort of deterministic behavior is what? The only way in which you can have a sort of deterministic behavior is by statistical averaging of the governing equations, because the statistically averaged behavior will be sort of deterministic, but otherwise each simulation may be like a sort of random experiment where slight deviation in the initial condition or the boundary condition may trigger a large change in the final outcome. So statistical averaging is the only important practical resort, and that is why we try to develop the statistical basis or the statistical description of the turbulent flows. With that background, what we will try to see is that how we may statistically average the governing equations, that is the Navier-Stokes equation as an example. So we will now see the method in which you average the Navier-Stokes equation, and since Reynolds contributed a lot towards that, we also call these as Reynolds averaging process. The Reynolds averaging process starts with the basic form or the well known form of the governing equations. For example, we start with the continuity equation. So let us assume that we are dealing with a case when the density is a constant. That means you have the continuity equation as this one. So in the first step what we do is we decompose the variable, here the velocity is the variable, into two parts. One is the mean and another is the fluctuation over the mean. When we say mean, we are not getting too specific that what type of mean, but as we discussed earlier that it may be, for example, time average, space average or ensemble average, but here we are just but we are basically dealing with some sort of averaging here, and that averaging is what is going to give rise to some equations in terms of the average quantities. the way in which we derive the equations is very straightforward. So, we substitute this uj in the continuity equation. Once we substitute that, what we will get? We will get this equal to 0, and the next step would be to make an averaging of this equation. That means you average each of these terms. So, if each of these terms is like time averaging, then what you are basically doing? So, when you are time averaging a variable, then you are basically multiplying that with dt, integrating it from say time equal to t to t plus capital T divided by the time period in the limit as t tends to infinity. We have discussed that this infinity is notional, that means it is a time scale much larger than the individual small time scales of turbulence fluctuations. So, that operation when we are doing, we have to see that what is the consequence. The consequence for the first term is straightforward because it is already average. So, average value of the average is that is itself. Now, if you look into the other term, we have to basically understand that what will be the averaged in terms average quantity of this after doing the differentiation. So, we had earlier discussed that if you have say for example u prime and the average of u prime is 0, that we have shown very easily. The question is, what is the average of the derivative of u prime, and to do that basically we have to just use the limiting definition, the definition of the derivative in terms of limit. So, you can say that what we are looking for is that uj prime average at times, or say here it is the spatial average. So, at xj plus delta xj minus uj prime average at xj divided by delta xj in the limit as delta xj tends to 0. And see, individual constituents of the limit are the fluctuations and the averages are 0, no matter the averages are evaluated where. So, this therefore will become 0, and hence we come up with the average continuity equation. And once this is satisfied, if we substitute it back to the original continuity equation, then what we are left with is that the fluctuation components also satisfy the continuity equation. So, that is one of the important things that we will remember. Now, with this technique of averaging, we will next look into the averaging of the Navier-Stokes equations. Let us say we first write the I momentum equation, that is the linear momentum conservation or general momentum conservation in the ith direction. So, we write rho we have not written the body force, but if there is some body force you can always add beyond this. So, what we will do the same thing as we did for the continuity equation. So, substitute each term in terms of its average plus the fluctuation. When we do that, what we get in the next step? So, this is what we get as the left hand side. This equal to the right hand side, again we decompose all those terms in terms of the mean and the fluctuation. Just as what we did for the continuity equation, the same thing we will do, that is we will now do an averaging of each of these terms. So when we do an averaging over each of these terms, some of the terms come out to be very straightforward. For example, this first term, it becomes just itself, there is no change. The second term, we have seen that the derivative operations commute with the averaging operation. So we can take as if we find the time average of ui prime or maybe ensemble average of ui prime and find the derivative with respect to time. One of the important things is that averaging operation is not conflicting with these t. Why? Because the time scales over which we are averaging are different for the time scale for turbulent fluctuations and the time scale for the system level fluctuations. So although you have a sort of time scale involved with the averaging of ui prime and the time scale involved with the differentiation with respect to time, these are over two different scales and ranges, so they do not conflict with each other. So here when this is averaged, this averaging will give that this term will become 0. When you come to the third term, so let us look into the simplification of this third term a bit more carefully. So if we consider this third term, which is this particular term, so it is uj then del xj of ui bar, averaging of that, plus uj So we have just split it into 4 terms, and once we have split it into 4 terms, it is possible to simplify it quite conveniently. First of all, when you do the averaging operation, this is like a constant for the averaging operation, it remains as it is, the derivative commutes with respect to the averaging and the average quantity is there. So that means it just remains the same as it is. So this becomes uj bar del ui bar del xj. When you come to the next term, you see that you have one uj average which remains as it is after averaging, then the derivative commutes and it is taken to be independent of the averaging. So it is basically dependent on the averaging of ui prime, which is 0, and therefore this term will become 0. By similar argument, the next term will be 0, but the fourth term, there is nothing to believe that the fourth term will be 0. It might not appear to be so intuitive that why it may be non-zero, but we just have to keep in mind that the average of u prime is 0, maybe average of u prime is 0, but what is the average of u prime v prime, and that in general there is no basis for us to conclude that it will be 0 always. There are certain special cases in which this will be 0, but there are certain cases when this will be not 0. On the other hand, like if you are talking about the same variable u prime square with an average, so ui prime uj prime with j equal to I, that is anyway never 0, and we will see soon why. Now when you come to the last term, see we may manipulate with the last term by adding one extra term. What is that extra term? Let us say we add the following term. let us say we add uy prime this one. Adding this extra term is as good as adding 0, because from the continuity equation we concluded that the fluctuation component of the velocity satisfies the continuity equation, that means this term is itself 0. So whatever is multiplied with that and average, that is also 0. The advantage that we have gained now is that you may combine these two terms and write it as nothing but this one by the product rule of differentiation. So to summarize, when we have simplified the left hand side, we have got a term which is exactly of the same form as that what we have got even without averaging, plus we have got an extra term here, and this extra term is something that we have to keep in mind while simplifying it further. The right hand side is something which is again much more straightforward. So if you have the first term is same as itself because it is already averaged. The second term will be 0 because it will deal with averaging of a single fluctuation. The third term will remain as it is, and the fourth term will be 0 because it again involves averaging of a single fluctuation. So whatever we have got from the simplification after averaging, if we try to cast it in the form of the Navier-Stokes equation, but now expressed in terms of a statistically average description, let us see how it looks. So we have the left hand side, if we just keep it just as in the same form as the original Navier-Stokes equation, there was one extra term in the left hand side because of averaging, and that extra term we will bring to the right hand side. Here, since we have considered a problem where rho is a constant, so we can just take it inside and outside the derivative without any problem. The left hand side, you see, if the time dependence of the average velocity or the mean velocity is considered to be 0, that means it is considered to be a stationary turbulence or a steady turbulence. It does not mean that the flow is turbulent, only statistically average behavior is, it does not mean that the flow is steady, it just means that the statistically average behavior is steady. So here this term, existence of this term or non-existence of this term, in either way it is unsteady. The unsteadiness is always there with the fluctuations, but when you have averaged it out, then if the average quantity is independent of time, that is if this term is 0, then we say that the turbulence is a stationary turbulence or sort of steady turbulence. Steady turbulence is a misnomer, of course, because turbulence cannot be steady. So sometimes stationary may be a more convenient term, but just it is a matter of terminology. Now if you see that what is the term in which this equation differs in form from the non-averaged Navier-Stokes equation, and that is with this last term, which actually was the extra term that was there in the left hand side. And we will try to understand first of all that what is the mathematical nature of this term, and then we will try to get a physical feel of what is the physical origin of this term or what could be the physical origin of this term. So mathematically, if you see that the term here, if you consider this particular term, this term has originated from the shear stress in a Newtonian fluid. On the other hand, the term which is there inside, we cannot conclude that it has originated from a shear stress physically, but just by looking into the dimensions of these terms we can say that this term also has a dimension of stress, and that is one of the important mathematical characteristics of this term. Not only that, mathematically it has almost perfect resemblance with the stress, because this also requires, like the stress tensor, two indices for its specification. So the description of this uy prime uj prime average is given by a stress tensor which is known as a turbulent stress tensor or a Reynolds stress tensor. It is a tensor of order 2, and the name stress tensor comes from the physical resemblance of the stress tensor that we get for a case when we are writing either the averaged quantities in this equation or the non-averaged form of the Navier-Stokes equation. So if we want to write the tensor in the form of a matrix with all its components, so you have say minus rho if you take as common. So basically you have u1 prime square, u1 prime, u2 prime, u1 prime, u3 prime, we can see that there are 6 independent components and this is a symmetric tensor just like the usual stress tensor. So this is known as the Reynolds stress tensor or the turbulent stress tensor or turbulent stress tensor. Why turbulent stress? Because like this stress tensor has originated because of the turbulence in the flow, because of the turbulent fluctuations in the flow.